Our presentation is on the longitudinal effects on a Cessna 172 due to a change in the elevator angle. It is presented by Nikita Petrushev and Josh Lead. Controlling an aircraft can be very complex. This is why we trust only certified pilots to fly planes. There are many switches and levers that make flying very complicated. For this analysis, we focus on the flap on the back of the airplane. This flap is called the elevator. The elevator is a control surface that is hinged to the rear of the airplane. It is crucial to the flight path of the airplane. In this problem, we will study the effects of how a change in the angle of the elevator can affect the flight dynamics of an aircraft. It is important for pilots and future pilots to understand everything about an airplane's dynamics, and this includes the effect of the elevator. Before we dive into the modeling, let's go over some background information about aircraft. An airplane has four forces acting on it during flight. These include lift, thrust, drag, and weight. Thrust is what moves the plane through the air. It is generated by the aircraft's engine by some type of propulsion device. Sometimes it's a jet, but in our case, a Cessna 172 aircraft generates thrust through a propeller. Lift is the force that keeps the airplane in the air. It is perpendicular to the thrust force. The main component in an aircraft that produces lift are the wings. Drag is the resistant force of an aircraft moving through the air, and weight is the force due to gravity. An airplane also has three axes it can rotate on, as pictured on the right. For our study, we will negate the roll axis and the yaw axis and only focus on the pitch axis. In a small fixed-wing aircraft, the flaps are controlled by either of the control wheels. The control wheel actuates specific linkages which adjust the flaps on the wings and the rear of the airplane. Shown in the bottom right is the cockpit of the analyzed airplane, a Cessna 172 aircraft. The plane we used for our study, as stated earlier, is a Cessna 172. It is a very popular, small aircraft that was first flown in 1955 and continues to be in production today. Shown are some of the specifications of the plane and the coefficient factors used when solving the system. All of the coefficients were derived from equations or graphs. Some of the more important specifications include the weight of the plane, the wing area, and the cruising speed. The drag coefficient and lift coefficient were acquired from the following tables and graphs. For simplicity of the study, the angle of attack was assumed to be 10 degrees for the acquisition of the aerodynamic coefficients. The moment coefficient value was retrieved from this plot. For the simplicity of the study, some of the following assumptions had to be made. First of all, we assume that the plane is traveling at a constant velocity. We also assume that at this constant velocity, the plane is at a constant altitude. We also find that the pitch angle will not be affected by the velocity. As stated earlier, the four main forces that act on an aircraft are lift, drag, thrust, and weight. The following figure shows the specific direction that each of these forces act. For this analysis, the plane will be in the position shown, but if the plane was dropping down, the forces would be acting in a slightly different angle. No matter the orientation of the aircraft, there is a relation to the direction of these forces. For example, the drag force is always in the opposite direction of the velocity of the plane. The lift force is typically perpendicular to the longitudinal axis of the plane, and weight is always straight down towards the earth, while the thrust force is parallel with the longitudinal axis of the plane. The angle between the drag vector and the thrust vector is considered to be the angle of attack. The angle between the main x-axis and the thrust is the pitch angle, which was studied in this case. The input to the system is the elevator angle, which is shown in the diagram and is measured from the longitudinal axis. An airplane flying in air is a very difficult system to analyze with many equations. For this reason, simplified equations of motion were used to solve the system. These equations contain constants that are shown that change based on the flight conditions, speed of the aircraft, and even geometric factors. For this analysis, the plane is flying at a constant velocity of 188 miles per hour. This so happens to be the maximum speed of the studied aircraft. The constants were calculated and plugged into the three simplified equations of motion. Our analysis was based off of these three equations. The input to the system is the elevator angle, which is considered to be delta in the equations. With this input, we obtain three outputs, which are pitch, which is theta in the equations, angle of attack, which is alpha, and pitch rate, which is Q. After plugging the values into the equations of motion, a state space model was used to analyze the dynamic system. The following shows the two state space matrices. The system was then simulated in MATLAB, and the response was graphed. Shown here is the step input of an elevator angle in the upward direction with respect to the longitudinal axis over a 20-second period. This input will be used in simulation to analyze the pitch angle, pitch rate, and angle of attack as a function of elevator angle and time. Note that after 20 seconds, the elevator reaches an angle of approximately 1.7 degrees. As seen in the graph, the pitch angle follows a very similar pattern as that input elevator angle. However, the pitch angle is very sensitive to a small change in the elevator angle. For instance, after 20 seconds in the previous slide, we found that the elevator angle had reached an angle of 1.7 degrees, while here we see that the pitch angle at the same time reaches approximately 11 degrees. The pitch rate plot is very similar to the pitch angle plot. You notice that the pitch rate is very low for this application. The more the elevator angle, the higher the pitch rate. Based on the following plot, it is concluded that the pitch angle is very sensitive to small changes in elevator angle. The plot shows the pitch angle and elevator angle as a function of time. For future pilots or current pilots, the elevator is a very delicate and powerful control device for flying a plane.